Hi class, welcome to week 8 of Geo 108 Global Climate Change. This week we'll be learning about orbital scale controls on insolation. Now that's insolation with an O, not insolation with a U, right? Insolation with a U is what we use to maintain the temperature of buildings, right? Or to try to stay warm, to not lose a lot of energy. Insolation is the energy that is radiated from the sun, and it's an energy density, so it is energy over an area. And we're looking at insolation at the top of Earth's atmosphere and the different geophysical controls on those. In preparation for this material, please read chapters 8 through 10 in your Ruddiman textbook. Chapter 8 gives you an introduction to these orbital scale controls. Chapter 9 talks about how these controls impact monsoons. And chapter 10 looks at how these controls impact glaciation and ice sheets. Now, because you have 3 chapters to read this week, so it's a pretty heavy reading week, there's not a lab due. So please read the chapters and post to the forum by Friday, March 30th. And it's really important that you grasp these concepts because we'll be building on them for the rest of the semester. So take your time going through the reading. Please make sure you post to the forum and think about some of the questions I put in the forum prompt while you go through. Now, we'll be looking at these geophysical controls on insolation. So remember, insolation is the radiation density at the top of Earth's atmosphere. Now, Earth, we know, is tilted on its axis. And it's tilted at 23.5 degrees from the ecliptic. The ecliptic is the orbital path that Earth follows around the sun. Now, if we didn't have a tilt, we would not experience seasons on Earth. Seasons are due to Earth's tilt. So if we have radiation coming in from the sun, and Earth is tilted in this way, the radiation is going to be hitting the southern hemisphere. The energy is going to be hitting the southern hemisphere more than that of the northern hemisphere. And so in the southern hemisphere, that would mean that we have summer, whereas in the northern hemisphere, we'd have winter. Now, as Earth rotates around the sun, on this side, here's our sun, my hand. The northern hemisphere is tilted toward the sun, and the southern hemisphere is tilted away. So that means that we'd have summer in the northern hemisphere. Now, these dates where we have, for example, in the summer on June 21st, we have the longest day in the northern hemisphere and the shortest day in the southern. So that marks the summer solstice for us in the northern hemisphere. Whereas the reverse, on December 21st, we have the shortest day in the northern hemisphere, which marks the winter solstice, but that's also the longest day in the southern hemisphere. Now, when we're at an in-between part of Earth's orbit about the sun, and the sun is hitting where we have the tilt going to the side, when the sun is heating both the northern and the southern hemispheres equally, we have an equinox. So those happen on September 22nd and March 20th. So that's where we have equal length days with latitude north and south of the equator, equal heating. All right, so that is what brings about the seasons. Now, throughout geologic time, Earth's tilt is not constant. It varies between about 22 degrees and 24.5 degrees at its maximum. So just think about how that would impact the seasons and what they look like, right? So if we have a greater tilt, we're going to have more extreme seasonality throughout the year. Whereas if we have a less extreme tilt of like 22 degrees, we're not going to have the same extreme seasonality. And that's not the only thing that varies for the Earth. The Earth, just like, so the Earth rotates, right? One full rotation is a day, and I'm spinning it the wrong way, but you get the point. It takes a day to complete a full rotation. And because it's rotating like this, and because of the friction caused by the moon, right? Because the moon and Earth and the sun, everything's gravitationally attracted to each other. And because of this friction from the moon, Earth is slowing down as it rotates. So just think about when you spin a top. It's going pretty steadily. But as it starts to slow down due to friction, what happens? It wobbles. It wobbles about on its axis. So Earth, as it rotates, it's actually slightly wobbling. Yes, Earth is wobbling in space. So it's slightly wobbling, and that wobble is known as axial precession. And so this Earth's wobble, its precession, also varies throughout geologic history. So its tilt varies on about 40,000 year cycles, and its axis precesses on about 22,000 year cycles or so. So that actually causes the seasons to change when they happen throughout the year. All right, so like at a midway point, we'd actually be experiencing summer in the northern hemisphere in like December, okay? At about like the 10,000 year mark or so. And so in the posted content, we're going to be looking more closely at some of these orbital scale controls on the amount of insolation that Earth receives at the top of its atmosphere. I have some videos posted on, first I'll be going through cycles and the sine wave, just so that it's a little easier for you to visualize that. And then I have a video on what a day is, the difference between sidereal and solar days and years. Then I have several Van Biesen videos that I think are very clear on some of these motions of Earth and these orbital scale controls. And I'll annotate a couple of the figures from Ruddiman on monsoons. Then I have a NASA video showing you real satellite data looking at monsoons over Africa. And finally, there's a last video looking at these orbital controls on ice ages, and these controls are known as the Milankovitch cycles. So please go through all of that, post any questions you have, and enjoy learning about these orbital scale controls on climate.